we want to know the stiffness K of the spring. If we're in static equilibrium as pictured. I guess in this one, that's all we want. We want to know what must the stiffness in this spring be such that in this picture and under those conditions that we're in static equilibrium. We are given that the rod AB has a weight of 15 pounds. Very often in these rigid body problems, whether it's 2D or 3D, we will be ignoring the weight of the object. Normally it's very small compared to the other forces that act on it, and it really doesn't change our solution that much. In this case, though, we are given its weight, so we will include it, because we see there are no external forces acting on this. It's just kind of resting there, and then the spring is propping it back up. So the weight will matter in this problem, and luckily we're given what the weight is. The spring is unstretched when theta is equal to 0. So we can actually do the math right here. If the spring is unstretched when theta is 0, what does that tell us about the spring? If we turn that up to 0, that theta to 0, then the rod is horizontal. If the rod is 3 feet, if that whole span is 6 feet, that means that the spring must have originally been 3 feet. Again, they tell us that when theta is 0, it's unstretched. So that 3 feet is that original length. I'll call it L naught of the spring. Our first choice, that again, it becomes a little bit harder in these rigid body problems. What is the object that we're going to be isolating in our diagram? The rod AB, we'll see once the free body, in retrospect, it will be obvious. It's not necessarily up front, but the rod will be a better choice in this case. So I'm going to take that greenish rod and isolate it from all of its connections. So in this case, what are the forces and or the moments that will act on the rod? It's isolated. I've removed it from the pin. I've removed it from the spring as well. Actually, we know that that's going to be 30 degrees because that was given to us, which I guess I should have put here too. Yeah.
We have the tension of the spring.
Right. We can at least presume the spring is in tension. It could be in compression. That would be okay. I'll assume tension here. So the force in the spring, I'll call it Fk. Right, what other forces? Right, in this case, we do have to worry about the weight of the rod. It weighs 15 pounds. Where can I draw the weight of the rod?
The center.
Right, because we're told it's a uniform rod, then its weight, we can just simplify into saying all of its weight acts at its center. In Unit 3, we'll be talking about non-uniform objects and how we can find where their center of mass is. But for the uniform, it's just acting at its center. So the 15 pounds from its weight acts at the center of the rod. Other forces and or moments that act on the rod. Pin at A. So remember that we've removed that support, so we have to model what did that support do to our rod. For the pin, pins are all in 2D always going to be the same, but it prevents the translation left-right and up-down. It allows for rotation though, so the two translations it prevents, I'm going to model as a force, I'll assume in the positive x, and a force in the positive y. They're not necessarily in the positive x and positive y, but I find it easiest for consistency to just follow the same direction as my coordinate system. Right, so force of 15 from the weight, force from the spring, and the force from AX and AY. So looking at the free body diagram, what is missing from it before I can write all of my equilibrium equations? We don't know yet its orientation. I need some angle or some way of knowing where f of k is pointing. Fk is pointing. Otherwise, I don't know how much is along the x, how much is along the y. So that piece is still missing from my free body diagram. So I'm going to actually find that first before drawing my free body diagram. And actually, another diagram is going to be helpful here because we will see when we get to the equation step, right, we want the current length of that spring. So this second diagram will actually serve two purposes. So in the second one, this is just going to be drawing the geometry. It's not a free body diagram, but I want to draw what this triangle looks like. And it's not meant to look isosceles. So I have the rod I know is 3 feet. I know that this has to be 6 feet. So things I don't know that I will need to know, the current length of the spring, because I'll need that for Hooke's law, which will come later. I wouldn't necessarily need that for the equilibrium equations, though. But I will need that eventually anyway. And I also want to know the orientation of that spring. In my notes, I just called it beta. Due to these being alternate interior angles, if I find the beta up here, I will also know the beta down here. And I would be able to fill in that information then in my free body diagram, and then I can go and write my equilibrium equations from there. So this length of the spring and the orientation of the spring I need to find. I'll start here because, again, my free body diagram is not complete, so I can't write my equilibrium equations yet. How can I find either beta or L prime using that second diagram?
You can do law of cosines to get the length.
Right, law of cosines. This goes back to what we did at the beginning of the class, going back through that trig. Law of cosines will give us that unknown length L prime. If I choose L prime as my left-hand side, since I know this 30 degrees, I'll have enough information from the rest of it to solve for L prime. So it'll be the a squared plus the b squared minus 2ab times the cosine of 30 degrees. Since my only unknown here is L prime, I can use equation 1 to find L prime. And L prime, 3.72 feet. I have L prime. I want to find beta. How can I find beta? Right, I can use, law of cosines I could use again. Here I would trust law of sines because I know that the 3 is not the largest side in my triangle. If I wanted to find this angle, then it could be obtuse. I think it does turn out to be obtuse in this case. If an angle could be obtuse, that's where the law of sines could fail you, and that's where you want to use law of cosines. But the obtuse angle, since you can only have one obtuse angle, it could only be opposite the longest side, which we know is the 6. So law of sines is fine to use here. So the sine of beta over its opposite side of 3 is the same as the sine of 30 over its opposite side, which we just found, 3.72. The only unknown is beta. We get 23.8 degrees. So actually, this angle is obtuse, but it is not going to really matter for this problem. All right, we have beta, we have L. Actually, I can now put the beta here. I know this is 23.8 degrees from the horizontal. Now my free body diagram is complete. I now have enough information to write my equilibrium, my 3 equilibrium equations, because I know the orientation now of all of my forces. Now I use my free body diagram. I can get 2 force equations and 1 moment equation. The order I do them in really doesn't matter. Let's just say we usually, though, want to get numbers as soon as possible if we're solving it by hand. What equation could we use first that will give us one of these 3 unknowns, ax, ay, fk? What equation will give us one of them right away? We go to the moment equation, and specifically the moment around point A. For this problem, ax, ay will not be in that equation. Only fk will be in that equation. So if we choose the moment around A as our moment equation, we get one unknown and we can solve it right away. Again, the order doesn't matter. You can get the right answer no matter what. You can get a solvable system of equations. But kind of efficiency-wise, starting with the moment gets us numbers right away and makes our lives a little bit easier from a solution standpoint. So I would say in this problem, if we start with the moment equation specifically around A, that's the most efficient place to start. it's not the only, it's not a unique play, it won't give you a unique answer. Or it does give you a unique answer, but it's not the only way to get that one answer. Okay, so if we sum the moments around A, AX, AY pass through A, so they're not going to be in this equation. The weight will be in this equation. So it's going to be a magnitude of 15 pounds. And how far is the 15 pounds from point A? Is it 1.5? This distance is 1.5, but that 1.5 is not the perpendicular distance between the weight and A. Right, 1.5 cosine 30 gives us just that distance here. So that's going to be the perpendicular distance between this vertical force and A. So 1.5 cosine 30, is that going to be a positive or a negative moment around A? Right, it's counterclockwise, and that's positive. Right, so the 15 pounds is taken care of. Now we have the spring force. This will have a horizontal and a vertical component that I want to break it up into. I'll start with the vertical component. That will be Fk times the sine of 23.8. And what is that vertical component's distance from point A? So that will be, if it's the vertical piece, it's this distance, so it's not sine 30. Right, this will be 3 cosine 30. Again, the diagonal distance is 3 feet, but we only want the perpendicular distance, so we're looking for that horizontal dimension. So 3 times the cosine of 30 will give us the length between A and this point here. So the vertical component will get multiplied by 3 cosine 30, and this creates a negative moment around point A because it will be clockwise. We then have to look at the horizontal component, which will be the Fk cosine 23.8. The horizontal component, we're now looking at this as our perpendicular distance. So what will that distance be between this horizontal component of Fk and point A? Right, so here it's opposite the 30, so it's 3 sine 30 degrees will be that distance between A and the horizontal component of Fk. Now make sure you keep track of what we're looking at here. This is the distance. This piece of it is the force. So it's still the force times the distance, but we're looking at just a vertical component of the force and then a horizontal distance, horizontal component of a force, and a vertical distance. Now, and going back to the horizontal piece of Fk, will that be positive or negative around point A? Right, if we hold it at A, it's going to cause the structure, if this were a piece of paper, the paper would be spinning clockwise, so therefore this is also negative. Because we decided to start with the sum of moments around A, and specifically at A, Fk was the only unknown here, so from equation number 3, we can right away get the value of Fk. And we get that to be 8.05 pounds. For the purposes of this problem, I will solve for Ax and Ay, but actually to answer the question, what is the value of K, do we need to know Ax and Ay? Right, we can, actually I'll go to there now, I'll add the rest of them later. We could jump to Hooke's law right now. We know that the sum of, or the force in the spring is its spring constant, which we don't know. Actually, because I know the value of Fk, that's 8.05. And that's the unknown value of K. its current length, we determined L prime up here, or here, 3.72. Originally, though, it was only 3 feet long, so it is in tension. So since we know everything in equation 4 except for k, we can find that value of k. So k, from equation 4, 11.2 pound per foot. So again, for the purposes of really what we're asked to find, we would be done here. If this were an exam, these are all the equations you would need. We didn't need to find the sum of forces x or y. But since we're still going through these, we will go through those steps here. But normally, we could be done now. But I want ax and ay. This is where now I can sum forces. Again, I want to reiterate, summing moments we did not have to do first, but it did have the easiest path to a solution. If we sum forces first, as we're about to see, we have ax to the right, and to the left we have sum of f sub k. 23.8. So you can see here, if we start with this equation, there's 2 unknowns in it. So if it's our only equation, we can't solve for either of them. That was different than the sum of moments equation, which only introduced one equation for that one unknown. At this point, and this is an important thing to look at, even though I know the value of fk, whenever I write equilibrium equations, I'm only basing it on my free body diagram. I'm still calling it fk when I write this. Now, I will put in its numerical value of 8.05. I would recommend against starting with the numerical value. It's easy to make a sign error, as we're going to see later, especially if one of our values turns out to be negative. It's very easy to make a sign error here. It is negative. It's minus 8.05 cosine 23.8. It would have been easy if we started with 8.05 to say, oh, it's negative. We're adding 8.05 times cosine 23.8. That's why, again, start with the free body diagram to make the equation, then fill in values that you found. At this point, now that we do know fk, ax is the only remaining unknown in equation 5. Ax has a value of, if I can read my writing, I believe it's 7.36 pounds. So it was a positive value. I assumed it was to the right. The positive confirms that. So ax does pull it to the right. In turn, that would mean that it is pulling the pin to the left. And I can get ay then if I sum forces in the y direction. I have all of ay. I have the weight of the bar pulling down. And I have now sum of fk sine 23.8 in the upward direction. Again, I now can fill in that's 8.05. And from equation 6, the only remaining unknown is ay, which also turns out positive, 11.8 pounds. It's positive. My assumption was correct. It is pointing up.